Hello and welcome to my video series on the Modular Breeding Program Simulator. In this video I will walk you through the basics of our web-based interface. And for this I've already loaded in our login page where you can enter your username and password. In case you do not have an account so far, you can use our guest login, which will provide you with an account that is not allowed to use our computational resources, but should be fine for testing. For now, I will enter my own login details, press the login button, and will be redirected to the actual input stage. Here I can enter the details of my breeding program. For now, I will load in one of our templates that are accessible here via exemplary templates to already have like a pre-filled in template to work from. So let's say we want to start a simulation with some cattle. Here we can provide a variety of information. So first up, we provide some general information. The project name is still from the template. Let's say we want to do some cattle breeding program. Next up, it's asking for if we want to work with some advanced settings. Here you have quite a few additional settings to activate, like activate parallel computations, activate some additional modules to simulate culling or economic parameters or those kind of things. For now, I will skip on this. Next up, as we've loaded in a template, we already have reasonable inputs here. As a species, cattle is selected. All breeding actions are kept in the time unit of month, and as the underlying genomic data, data from an LD chip was loaded in, but we only want to work with 10,000 markers. Next up, there is a module on available phenotypes. Here there are already 3 phenotypes entered: milk, fat, and protein, which with reasonable values for their phenotypic mean, their phenotypic standard deviation, their heritability, and the number of underlying QTL for each of those traits. For milk and fat, there is also a major QTL added in the position, which is called DGAT, which is responsible for 0.5 fat percentage, and availability of that QTL leads to 800 liters less milk. In terms of correlation, they have already been entered in terms of the residual correlation and the genetic correlation between the different components. Next up, there's a selection index. Here the only index defined so far is one with equal weighting on milk, fat, and protein. We could, for example, define a selection index called focus milk. And let's say this particular index is designed to put 3 index points on milk, 1 on fat, and 1 on protein. The next information we have to provide is how those indices are standardized. The default is that they are standardized by unit. As milk has a much higher range than the other trait, it's probably makes sense to use some standardization based on the phenotypic or the breeding value standard deviation. I'm just selecting the breeding value standard deviation here. Next up, it's asking us for phenotyping classes. The one phenotype class provided here is one where phenotypes are generated for milk, fat, and protein, which is realistic for cows. As bulls typically do not give milk, we should enter here a second phenotype. Let's call that bulls. And for bulls, we do not have an observation for milk, we do not have an observation for fat, and we do not have an observation for protein. Here we're using a binary coding of like 0 is not phenotyped, 1 is phenotyped. In case you would enter a higher number here, those multiple observations would be handled as independent observations. So your residual variation would go down here. And this is basically all you have to provide as prior information. Next up, we would go into our interactive environment where you can draw your breeding program itself. Each breeding program contains of nodes and edges, where a node is representing a group of individuals and an edge is representing a particular breeding action. So we are activating our environment by pressing here the edit button. And now we have the option to either add nodes to our graph or add edges to our graph. Let's say we want to start with some founder animals, so I want to add a node. I would just press the add node and press somewhere in our interactive environment. And we are here getting this pop-up window where we can provide information about the node we want to generate. So let's say we have a node called bulls, which contains 50 individuals. Those are founders of our population, so this needs to be checked. And as it's a founder cohort, it's asking us now how the genotypes of this cohort are generated. On default, this is done via random sampling. Alternatives would be to upload some genotype data here, or some different sampling approaches to generate fully homozygous, fully heterozygous lines, and so on. Let's stay with random sampling so far. Bulls are male, and their phenotyping class is bulls, meaning we won't generate any phenotypes for this class. Next up, we want to generate a second cohort containing of the female side, so we want to generate some cows. Let's say we also have 50 cows, and those are female, those are also founders. We also pick random sampling, and the phenotyping class is the already defined default phenotyping class, which is phenotypes for all different traits. Next up, we have this as a starting point and can think of what our breeding actions typically are. In a cattle breeding program, it's quite difficult to apply selection on the female side, as cows are limited in their reproduction. So let's say we want to start with the 50 bulls and reduce this cohort to the top 10 bulls that are used for reproduction. So let's say we add a node, call these bulls selected. And let's say we want to reduce our cohort size to 10. Those are also male, and we again do not have any phenotypes for this group. Next up, we have to tell the tool how to link those two cohorts, and this is the first time we have to generate an edge. For this, I'm pressing the Add Edge button, and next up, draw an arrow from where I want this arrow to start to where I want it to end. So I press on the bulls node and draw an arrow to the bulls selected node. Here it's again asking us what kind of breeding action we want to use. So here I'm selecting selection. How long does the selection procedure take? No time at all. As a selection type, the default was random. We do not have any phenotypes, so it probably makes the most sense to here use a breeding value estimation. And for this breeding value estimation, we have to provide additional information. So, for example, what kind of method to use. This is basically all sorts of different R packages that are available to do such thing. I will here just use our default fast model. As a selection index, we can here select whichever focus we want to use. So either the focus on milk or, let's select the focus on milk. The selection proportion is automatically calculated. So the last thing we have to provide is information about how the relationship matrix in the mixed model is derived. And for this, as we have genotype data available, we'll just pick the Van Reyden relationship matrix. Also, we have to provide which cohorts to use in the breeding value estimation. As this is a very small example, I would just tell the tool, you use all available data. And with this, after pressing the save, we have added our first breeding action to the tool. After this selection is done, the next logical step would be a step of reproduction. For this, we want to generate some offspring by doing reproduction between the group of select bulls and the group of cows. Let's say we want to have 50 offspring bulls. So offspring bulls, 50. Those are no founders, those are male. We do not want to phenotype them, and that's it. And we start our reproduction act again by drawing from the parent node to the child node. The breeding type now is reproduction. Such a reproduction cycle typically takes 12 months. It's here asking us for some information on the second parent. The second parent is supposed to be cows. You don't need to use that. You can draw a second arrow in the same way as shown here, but this is just a procedure that automatically draws a second edge with the same properties. As we've generated male offspring, we also need some female offspring. The name of this cohort is offspring cows. Again, 50 individuals. Those are female, and they are from our default phenotyping class. The same procedures on the male side for the edges as well. Again, we connect the parent node with the child node, select reproduction. This action takes 12 months, and the second parent is supposed to be cows. Save, and that's one generation of our breeding program we want to work with. As breeding programs typically are executed over a longer period of time, we have a special edge called a repeat edge to iteratively repeat such a cycle. So in this sense, I'm just telling the tool, use the offspring cows and use those as the new input to cows. So here we are selecting the type repeat and telling the tool repeat this particular cycle 10 times. We do the same on the male side. So the offspring bulls are supposed to be the input for the bulls cohort. This is a repeat action that's supposed to be executed 10 times. And with this, we have entered a breeding scheme for 10 generations of cattle breeding. With this, everything is set, and we can now save our breeding program via the Save Project button, and are basically done with everything we have to enter. Next steps would be, in case you have a guest account, to export the project, which will generate a download link that you can then use as an input for our R package. Or, as I have a user account, I can now scroll down and press the Start Simulation. This will contact with our server at the University of Göttingen and automatically simulate the breeding program there. I mean, as this is a rather short example, simulations are already done, and after everything is finished, you now have the option to look at the details of your simulation. So first up, you have a list of cohorts that were generated. So we are starting with a group of bulls. Those were 50 individuals generated at time point 0. We ignored all the economic things so far, so I will ignore this. And after scrolling down, you see all the cohorts that were generated and at which time point. The last cohort, the group of offspring cows, number 10, also contained 50 individuals, and it took like 132 months to generate those. Afterwards, you have a log file from the backend R simulation. This contains information on the accuracy of each breeding value estimation and provides you with warning in case something is going wrong. But for now, I will skip on this. As the simulation was a success, we do not have any errors, so everything is good. Next up, we are here providing you a module to download the RData object of the population that was generated. And in case you're interested in specific information, you can also just tell the tool what kind of data you want to export. So, for example, you could be interested in a VCF file of a specific cohort, say the offspring cows of repeat number 10. And after a preparation step in which the data will be collected, you can now just press the download VCF button to get your file. And let's see, here is your file, 1.5 megabyte, and it's basically a classic VCF file you can use for any follow-up analysis. You could also download some phenotypes here, or a pedigree file on basically everything you could imagine. In case something you want to export is not provided here, just tell us and we can add that into the tool. Lastly, we have some analysis functions of your particular breeding program to generate a plot of your phenotypes, your underlying genomic values for each cohort, the accuracy of your breeding value estimation, then some information about inbreeding and relation between and within cohorts, and lastly how the allele frequency in a particular major QTL is changing. So, for example, let's look at the genomic values and how they are changing. I will run this analysis, and I want to see how breeding values change for the cohort of say offspring bulls or offspring cows. Results are supposed to be plotted by repeats, and I will tell the tool just to generate a plot. And here, this is basically what the breeder wants to see. We start off with a milk production of 9.1 thousand liters of milk, and after 10 repeats of our breeding program, we end up with 10.7 thousand liters of milk. So quite nice. You could generate the same plot in terms of time or in terms of cohorts. This is particularly interesting in case you have overlapping generations or just more complex breeding programs in general. The same plots that were generated for milk are also generated for fat and for protein. Nothing too surprising here. It could be, for example, interesting to play a bit around with the selection indices and see what changes to a selection index will lead to which results in terms of what gains to obtain in which trait. Another thing we could have a look into is how the frequencies in the major QTL are changing. So I will run this analysis. I'm interested in results by repeat, and I want, as we only have one major QTL, I will select it here. The QTL was in milk, and its name was Degat. I want to again see the offspring cows, and I will plot the results, and it's now providing us with information on the allele frequency of the B allele. And we see even though milk production is negatively influenced by presence of the B allele, this is still rising in frequency. In terms of the observed heterozygosity and the expected heterozygosity, those are quite stable, so the QTL is far from fixation. This, however, is only a single simulation. In case we want to have like it's probably necessary to repeat this simulation multiple times to get to make quantitative statements on what kind of behavior to expect here, as this is underlying a lot of randomness. And with this, I think I've shown enough for now as a basic example of our breeding program. Thank you for your attention, and we'll be happy to see you in the next few tutorials in which I will go into more detail on all our advanced settings.